Have you ever wondered how we get so much power to big machines and entire factories? A lot of it has to do with something called a three-phase system. One of the coolest ways to set this up is the delta connection. So what is it? Imagine three electrical sources or phases that we need to connect together. In a delta connection, we link them end to end, forming a closed loop. If you were to draw it out, it would look just like a triangle. That's why it's named after the Greek letter delta, which is shaped exactly like a triangle. This simple but powerful shape is the key to how it works and what makes it so useful for heavy-duty jobs. Let's build one in our minds. Think of each of our three phases as a long wire with a start and a finish. Let's call our phases Phase A, Phase B, and Phase C. To create the delta connection, you take the finish end of Phase A and connect it to the start end of Phase B. Then you take the finish end of Phase B and connect it to the start end of Phase C. To complete the loop, you connect the finish end of Phase C right back to the start end of Phase A. Now you have a continuous, closed triangular circuit. There are no loose ends hanging out. Everything is connected in a self-contained loop, which is a very important feature of this system. So how do we get power out of this triangle? We attach our main power lines, called line conductors, at the points where the phases meet. These connection points are called nodes or junctions. Let's say the point where Phase A and Phase C connect is our first junction. We'll attach a line wire there. The point where Phase A and Phase B meet is our second junction, and we attach another line wire. Finally, the spot where Phase B and Phase C join becomes our third junction, with our third line wire. These three lines are what deliver the electricity from our delta system to the machines that need it. This triangular setup is not just for fun. It's designed for specific, power-hungry applications. You will most often find delta connections in industrial settings, where there are large electric motors that need a lot of power to get started. They are also very common inside certain types of transformers, which are devices that step voltage up or down for power transmission. The delta configuration provides a robust and reliable way to deliver a large amount of balanced power, which is exactly what these big pieces of equipment need to run efficiently and effectively day in and day out. It's truly a workhorse of the electrical world. Now that we know what a delta connection looks like, let's talk about the rules of electricity that apply to it. There are two main things we need to understand: voltage and current. Let's start with voltage. In a delta system, we have two types of voltage to consider: phase voltage and line voltage. Phase voltage is the voltage across a single phase winding, one side of our triangle. Line voltage is the voltage measured between any two of the main line conductors coming out of the junctions. Here's the simple and most important rule for delta. The line voltage is exactly the same as the phase voltage. So, we can write it as an equation: line voltage equals phase voltage. It's that easy. This unique voltage relationship is a defining feature of the delta connection. Because the line conductors are connected directly across the phase windings, they see the exact same voltage potential. Think about it. The line wires coming from junction A and junction B are connected to the two ends of the phase winding between them. There's nothing in between to change the voltage. This is incredibly useful in applications where you need to maintain a high, consistent voltage level to power your equipment. It simplifies calculations and ensures that the full voltage of the source is delivered directly to the load without any reduction. What about the current? The current behaves a little differently. Just like with voltage, we have phase current and line current. Phase current is the amount of current flowing through one of the individual phase windings, again, one side of our triangle. Line current is the current flowing through one of the main line conductors that goes out to the machine. In a delta system, the line current is always higher than the phase current. The rule is that the line current is the phase current multiplied by the square root of 3, which is about 1.732. We write this as line current equals square root of 3 times phase current. Why is the line current higher? It's because at each junction, the current from two different phases comes together. The currents from two windings combine to feed into a single line conductor. However, because the phases are out of sync with each other, by 120 degrees to be exact, they don't simply add up. The mathematical result of this combination is that the resulting line current is 1.732 times greater than the individual phase currents. This higher line current is a key characteristic to remember when designing and protecting a delta-connected system, as the wires need to be thick enough to handle it safely. Every system has its strengths and weaknesses, and the delta connection is no exception. Let's start with the good stuff. One of its biggest advantages is its reliability. Since the phases are connected in a closed loop, if one of the three-phase windings in a delta transformer fails, the other two can still deliver three-phase power. It won't be at full capacity, of course, but it can keep things running in an emergency. This is known as an open delta or V connection. Another great benefit is that delta systems provide a higher starting torque for large motors, helping them get up to speed quickly, which is crucial in many industrial processes. Another key advantage is that the delta connection does not have a neutral point. The system is made of just the three hot wires. This can be a benefit in balanced three-phase only industrial environments because it simplifies the wiring. You only need 3 conductors instead of 4, which can save on material and installation costs. This lack of a neutral wire is perfect for loads that are perfectly balanced, meaning each phase is drawing the same amount of current. This is often the case for large, three-phase motors or heating elements, which are the primary users of delta systems anyway. Now, let's look at the not-so-good side. That missing neutral wire can also be a major disadvantage. Without a neutral, you cannot easily power single-phase loads. Most of our everyday appliances, like lights, computers, and small kitchen gadgets, are single-phase and require a neutral wire to complete their circuit. This makes a pure delta system unsuitable for residential buildings or commercial offices where you have a mix of single-phase and three-phase loads. The system is really specialized for machines that use all 3 phases equally and don't need that neutral return path. Another drawback is the higher line current we talked about earlier. IL equals the square root of 3 times IP. Because the line current is 1.732 times greater than the phase current for the same amount of power, the conductors used for the lines need to be thicker and more robust. This can increase the cost of the wires. Furthermore, delta systems can be more sensitive to unbalanced loads. If one phase starts drawing significantly more or less current than the others, it can cause voltage instability across the system, which is not ideal for sensitive electronic equipment. It really shines best when everything is balanced and symmetrical. So where can we actually see these delta connections in action? Their unique properties make them perfect for certain jobs in the real world. One of the most common applications is in large industrial electric motors. Think about the giant motors that run conveyor belts, pumps, fans, and heavy machinery in factories. These machines need a huge amount of torque or rotational force to get started. The delta connection's ability to deliver high, consistent voltage helps provide that powerful starting kick, making it the preferred choice for this kind of heavy lifting in the manufacturing and industrial sectors. You'll also find delta connections playing a crucial role in our power grid, specifically in high-voltage transmission networks. When electricity is generated at a power plant, transformers are used to step up the voltage to extremely high levels for long-distance travel. This is done to reduce energy loss along the power lines. Many of these large power transformers use a delta connection on their high-voltage side. The system's robustness and efficiency at handling high voltages make it ideal for the task of moving massive amounts of power across the country before it is eventually stepped down for local distribution. A third very common place to find a delta setup is inside the windings of a transformer itself. Transformers often have different connection types on their primary or input and secondary or output sides. A very common configuration is a delta Y transformer. In this setup, the high-voltage primary side is connected in delta to handle the incoming transmission voltage. The secondary side is then connected in a different configuration called a Y or star, which does have a neutral point. This allows the transformer to supply power to both three-phase industrial loads and single-phase residential loads, giving us the best of both worlds. From the factory floor to the power lines crisscrossing our landscape, the delta connection is a fundamental building block of our modern electrical infrastructure. While you might not see the triangle shape directly, its principles are hard at work every single day. It's a perfect example of how a simple geometric design can be harnessed to perform incredibly powerful and essential tasks. So next time you see a large industrial motor or a big electrical substation, you can be pretty sure that a powerful little triangle, the delta connection, is working silently behind the scenes.